Ever think about what's protecting the incredibly complex electronics inside a pacemaker? Or the sensors in a self-driving car that just cannot fail? Well, it's not magic. It's actually this remarkable material that acts like an invisible suit of armor. So let's get into it.
Okay, just take a look at this. You've got a circuit board, fully powered up, LEDs are glowing, and it's completely underwater. I mean, that should be impossible, right? This one picture really gets to the heart of what we're talking about today, a practically invisible material that creates a totally impenetrable shield.
But to really appreciate the solution, you first have to understand the problem. You see, our most important electronics are in this constant, silent war with the world around them. And these are the invisible enemies right here. Moisture, that's the obvious one. It causes shorts, corrosion, all kinds of bad stuff. But it's also dust, tiny bits of debris, corrosive gases just floating in the air, and even wild temperature swings. All of this stuff just works to degrade and eventually kill the delicate components that run our world. And this just illustrates the stakes perfectly. On the left, you've got a normal circuit board after a really harsh salt fog test. It's toast, completely eaten away by corrosion. But on the right, that's an identical board that went through the exact same test, and it looks brand new. The only difference is a whisper-thin, invisible layer of protection. So what is this invisible armor? Well, this brings us to a really special class of materials that are designed to be basically the ultimate protective shield for our tech. They're called conformal coatings, and the name really says it all. It's this thin polymer film that perfectly conforms to every single nook and cranny of a circuit board. It seals it off from the outside world. Seriously, think of it like shrink-wrapping your electronics, but at a microscopic level. Now, there are a few different types of these coatings out there. You've got your acrylics, your silicones, your urethanes, but one of them, Parylene, is truly in a league of its own. It's kind of the superhero of the group. And Parylene has some absolutely incredible superpowers. It's not just thin, it's ultra-thin and perfectly uniform everywhere. Crucially, it's pinhole-free. That means it creates a true hermetic seal, so no moisture or gas can ever sneak through. On top of all that, it's chemically inert, it's an amazing electrical insulator, and it's even biocompatible, which means it's safe enough to put inside the human body. So how in the world do you apply a coating that's so perfect? Well, the way it's made is just as unique as its properties. You don't paint it on, you don't spray it, you don't dip it. And here it is. This is the secret sauce. While pretty much every other coating is a liquid, Parylene is applied as a gas, a vapor, and that changes everything. It's all done through this really cool process called chemical vapor deposition, or CVD. So picture this. First, you take a solid powder, and you heat it gently in a vacuum until it turns straight into a gas. Then you blast that gas through a furnace at over 550 degrees Celsius, which cracks the molecules into this super reactive form. And for the final step, this hot reactive gas fills a chamber that's at room temperature. And the moment it touches any surface, it instantly polymerizes, molecule by molecule. It literally grows a flawless plastic film on everything it touches. Now, as you can probably guess, that level of performance, it almost always comes with a catch. And with Parylene, there is definitely a price to pay for all that perfection. Remember how its greatest strength is being applied as a gas? Well, that's also one of its biggest challenges. See, on any circuit board, there are places you don't want to coat, like connectors. Masking for a liquid is easy. It's like damming a river. A simple barrier does the job. But masking for a gas? That's like trying to dam fog. That vapor is going to find and sneak through the absolute tiniest gap, which makes getting a board ready for coating incredibly tricky and labor-intensive. And the process is also incredibly slow. I mean, to build up a coating that's just a little bit thicker than a human hair, it can take about 15 hours inside that vacuum chamber. In the world of high-speed manufacturing, that is an eternity. This isn't a conveyor belt process. It's a slow, meticulous batch process. So all of this adds up to some pretty big hurdles. The raw material itself is expensive. The specialized vacuum chambers you need are huge investment. The process, as we said, is slow. And hey, what if you need to repair something that's been coated? Good luck. The film is so tough and chemically resistant, you can't just dissolve it. Removing it is a total nightmare, and you often need really specialized, expensive gear, like plasma etchers to get it off. Okay, so with all these major drawbacks, it's expensive, it's slow, it's a pain to fix, you might be thinking Parylene is this niche material that's probably on its way out.
But the exact opposite is happening. Demand for its unique brand of perfection is actually on the rise. And when you look at where it's being used, it all starts to make sense. We're not talking about your everyday consumer gadgets here. We're talking about fields where failure is just not an option. Electronics is the biggest piece of the pie, sure, but look at the other big users: medical, automotive, military, and aerospace. That tells you the whole story.
And the market data backs this up. It's expected to grow from about $170 million in 2024 to over $240 million by 2032. Now, that's not a massive market by global standards, but that steady, consistent growth shows that its special abilities are becoming more essential, not less. And what's fueling this demand? It's all the big tech trends that are shaping our future. As our electronics get smaller and more powerful, they also get more fragile. You think about life-saving medical implants, the hundreds of critical sensors in an electric vehicle, or the electronics way up high on a wind turbine. The need for the kind of ultimate failure-proof protection that only Parylene can offer is just getting bigger and bigger. And that really brings us to the final question here. The whole story of Parylene is a story of trade-offs. It's expensive, it's slow, and it's difficult to work with. But it's also perfect. And as we rely more and more on technology for our health, for our safety, for our entire future, what price are we really willing to pay for that kind of perfection?